Hello, it's I, Mr. Burkhart, sharing my screen with you here. Thought we could talk about some of this workbook stuff. I don't know where we left off. Carlos has got a pair of yo-yos, and they're modeled as solid discs with the rotational inertia of 1/2 mr squared. We're at the top of the stadium bleachers. They have a mass M and radius R, around with a string, and the mass can be ignored. He drops one yo-yo while he lets the other one unwind. So sketch a free body diagram for the dropped yo-yo. So that's this drawing over here. And it's just got the force of gravity. But the other yo-yo has got a force diagram of the force of gravity, but also a tension in the rope of a string pulling up on the edge. And that's going to provide a torque, right? We'll see what happens later. All right. So which yo-yo will land first? Well, I'm thinking the dropped yo-yo will land first because it's just being yanked down due to gravity, whereas the other yo-yo has got a tension force pulling up on it, slowing it down. All right, we're driving expressions for the time for dropping the yo-yo, the first yo-yo. It's our good old friend. Time is equal to the root of 2h over g. We've seen that before many times. Basically, if the initial position is 0 and the initial velocity is 0, then the displacement is equal to 1/2 at squared, and the acceleration is negative g. So you move the letters around. Also, we're going to use h instead of y, and you do some algebra, and that's what you get. We've done that before, but over for the second yo-yo, we've got a lot going on over here. Basically, for the rotational piece, the torque is equal to the moment of inertia times alpha, and the torque is equal to the tension force times the radius of the yo-yo. The moment of inertia is 1/2 mr squared, and then the acceleration in the alpha acceleration is equal to the regular acceleration, a over r. So when we do that, we can see that the r's are all going to cancel, and we're going to get the tension is equal to 1/2 ma. So basically half of the net force. And then if we look at if we go through a similar process using the net force equation, F equals ma, the difference in the two forces, the force of gravity minus the tension, is equal to ma in the y direction. And so mg minus the tension is equal to ma in the y direction. So now we substitute in 1/2 ma for the tension force. We got that from the rotational stuff over here, right here. And therefore, combining like terms, mg is equal to 1/2 ma in the y direction, or the acceleration in the y direction is 2/3 the acceleration due to gravity. So now the time to unroll is we go through this process, and we can see that substituting in 2/3 g for acceleration in this guy gives us the time to unroll of the square root of 3h over g instead of 2h over g. So that time is going to definitely be bigger, right? The square root of 3h is bigger than the square root of 2h. Each yo-yo lands on sticky tape and does not balance upon landing. Wow, that's a neat trick. In a clear, coherent paragraph, explain which yo-yo experiences a greater impulse due to the normal force from the ground. Well, I'm thinking the dropped yo-yo hits harder. Bam, right? Because it's going faster when it hits. It's got more kinetic energy. It's got more momentum. It's going to hit harder, and it's going to have more impulse. All right, now we're on H. So what's happening here is we have a hoop, and it's rolled down a ramp, and there's an angle theta, and the tabletop is H above the floor. The hoop rolls without slipping, and on the diagram below, we're labeling the forces, not components, that act on the wheel as it rolls down the ramp. So you can see there's a free space on bingo force of gravity pulling down. There's a normal force pushing up on the bottom of the hoop. So make sure that arrow is coming up off the bottom of the hoop, but the force of gravity is coming from the center of mass of the hoop. You see how they're not coming from the same place? So that's interesting. And then the force of friction is also coming from the bottom of the hoop. It said no slipping, so that's friction gripping the bottom of that hoop. So that's an interesting free body diagram. We've never seen anything like that. Sketch an energy bar chart for the hoop Earth system from the time when it's at the top. At the top, it's all potential energy due to gravity. You can see that. So that bar's filled in. And at the bottom of the ramp, it's got two kinds of kinetic energy. And they're showing that each one is even Steven kinetic energy. Now, is that a mathematical idea or just conceptual idea? Why would it have half of it be kinetic and half of it be rotational? Maybe we're going to find out later. But really, we do have formulas for those things: 1/2 mv squared and 1/2 I omega squared. And they're saying that those are going to be equal to each other. So here you go. Look at that. Derive an expression. Bippity boppity boo. So the energy at the bottom is all kinetic of two kinds. And there they are. There's the equations. Now, the momentum of inertia of a hoop is mr squared. So we would have to look that up. I don't remember that being given, but we could look it up. That's a pretty common one. And so also omega is v squared over r squared because omega is v over r. And that was some information we got at the front loaded in the beginning of this rotational unit. So now the r's will cancel, and basically, oh yeah, look at that. Both of them are equal to 1/2 v squared when all the m's cancel. So we can find that the velocity at the bottom of the ramp is the square root of GL sine theta. Look at that. That's kind of cool. Where'd that come from? Oh, because H is L sine theta from the drawing, going way back up here, right? This is L, and it's the hypotenuse, and this is theta. So H is the sine component of theta because it's the opposite to the angle. All right. H. Oh, we're still on H. Determine an expression for the distance d from the edge of the table to where the hoop lands on the floor. And so the time that it's in the air is 2h over g. That's we've been through that a million times, right? And now the distance is equal to vt. So we just derived v, and now we have t. So we can multiply these together. Since they're both under the root symbol, we can just smush them all together underneath the root symbol. Notice that g cancels, so that it doesn't really matter which way, what planet you're on, you're going to get the same result. The distance that it lands is related to the height and the length of the ramp, the height above the ground. So this h is not this. So I might have misspoke earlier. This is not h here. I don't know if you can see this, but this from the ball to the tabletop, that's not h. That's L sine theta. H is from the tabletop to the floor. So those two values will determine where the ball lands. Whoa, you've gone too far. So suppose a hoop is replaced by a disc with the same mass and radius. How will the distance land compare? It will be greater than because it has a smaller rotational inertia. So more of its mass is closer to the center. It's easier for it to begin to rotate. So less of the gravitational potential energy will be turned into rotational energy. Right. So it's going to have less, this is going to have more kinetic energy translational, which is going to give it more velocity, which is going to make it go farther. Collisions. Wow, this looks like that stuff from Khan Academy. I'm just looking at pictures. It looks like we have a round thing that it's going to hit some rods. And in case A, it's going to hit A, B, C, D. Okay. 4 pucks sliding to the right on the smooth table. Each puck collides with and sticks to a rod that can move or rotate with negligible friction. In all 4 cases, the pucks are identical, the rods are identical, the initial rightward velocities are identical, the final velocities of the pucks are perpendicular to the rod's lengths. In cases A and D, the rod is fixed to the table by a pin with negligible friction, but in cases B and C, the rod is free to move. So it looks like in B and C, the rod is going to get knocked over, right? And in D, it's going to spin around like a little paddle. For each case, determine whether angular momentum, linear momentum, and kinetic energy are constant. Put a check mark in the box if it's constant and an X if it's changes. All right. So they're saying in case A, the angular momentum of the So I think what we're defining the system as the puck and the bar together. So that means that both of those things are included in the system. Therefore, there's not an external force in the system. That therefore the angular momentum is not changing in the system of the angular momentum of the entire system is not changing. I think that's what they're saying there. That no matter where the puck hits the bar and no matter what the bar does, so you can see that this puck has an angular momentum. We talked about this in class and in Khan Academy. When it hits this bar, it's going to have an angular momentum of mv times the distance of the bar, the length of the bar, the radius of the bar. All right, so the linear momentum, they're saying that the linear momentum is going to change in case A and D. And in case A and D, what's happening is that these pucks have linear momentum, the bars don't. And then after the collision, some of that momentum is going to be angular momentum. And so that's what's happening. And the kinetic energy in every case changes because we're going to be changing the velocities. I don't know. That wasn't very good. Which has the most rightward linear momentum? A less than D less than B equal to C. Okay, so in B and C, they're the biggest. And in those cases, it's not going to spin. It's just going to knock the thing over. They don't lose any linear momentum. Oh, so we're ranking the most rightward linear momentum after the collision. They have the same linear momentum as the ball initially. Case A has no linear momentum after the collision. Just going to hit the bar, I guess. And D has a decrease in momentum in the rod puck because the external force from the axis is not negligible compared to the internal interaction. Oh boy, that's a lot of words. Oh, the balls are going to stick to the rod. I forgot that the balls were sticking to the rod. Okay, well then that makes sense. Right, and that's why the energy changes, because these are inelastic collisions. And when you have inelastic collisions, you lose kinetic energy. Boom, things get slower. So in case A, you're just having the ball basically stick into the bar. Nothing, it's just going to go donk, right? The bar's not going to move because it's stuck there on that rotational axis and we're not hitting either of the ends. Right, so bonk, yeah, that one's definitely going to lose some linear momentum. And the linear momentum is going to change. Yeah, okay, right. And then in case D, the bar's going to spin. In case B, it's not going to spin. It's just going to hit the thing and fall over. In case B, it's going to hit the thing and fall over. Okay. Most clockwise angular momentum. So A equal to C less than B equal to D. So A and C are equal and B and D are equal and A and C are less. And A and C are less because we're hitting the middle of the bar. Donk, right? And that's why we have less angular. And B and D are bigger because we're hitting the ends of the bar. And that angular momentum to start with is the mass of the puck times its velocity times the length of the bar. Doesn't matter where the spinning happens. Okay. We'll leave this here. J. Okay, this video is probably super long, so let's stop this and start a new one to make sure this worked.